Hello, what's up guys? Sir Gian again here. So welcome to another lecture series. So in this lecture, we're going to discuss integration by parts. And this is a part of a discussion in integral calculus. So integration by parts. So integration by parts. So suppose we have a certain function. So integrate this. So say for example, we have x e raised to x dx. All right. So if we let u be equal to ex, or we let x be equal to u, and then we take the derivative, we still arrive at the same equation. Wherein it still became a certain equation that we cannot integrate. All right. So for that case, if we're going to integrate this, so we can, it's hard to integrate this. So we'll find another way to integrate this, and we're going to use another technique, which we called integration by parts. And that would be the essence or the topic or objective of this lecture. So integration by parts. So suppose this is the original equation such that this would be our u and then dv. All right. So suppose if you can recall your differential calculus, so if we have product of two functions and we take the derivative of two functions, so let's name that as d dx f of x and then g sub x. So we know that the derivative of two functions or the product of two functions would then be equal to, so f of x d dx of g sub x plus g sub x d dx of f sub x. All right. So since this is additive, so we can reverse these two functions and these organs. So therefore, we can write this as g sub x d dx of f sub x plus f sub x d dx of g sub x. All right. So these are the rewritten form of this equation. Then, if we let these two functions be named as u and v, such that winning u be equal to f sub x and our b be equal to g sub x, and then d dx has a shorthand version of d, therefore, we can rewrite this as v du plus u dv. All right. So v du plus u dv. So we have here derivative of this, d of uv. All right. So derivative of uv, v du plus u dv. All right. So suppose we're going to reverse this equation, and we'll find the integral of everything. So let me erase everything that's written here. In one. All right. So we have here derivative of uv is equal to u, or rather v, derivative of u plus u derivative of v. All right. So suppose we need to take the integral of everything in our equation. So therefore, we integrate duv is equal to integral of v du plus integral of u dv. All right. So therefore, these two will cancel out so that we'll have uv equal to integral of v du plus integral of u dv. So we have u dv as our original equation. So therefore, we can transpose v du to the other side, or we can transpose everything to the left side, or further rewrite the equation as the integral of u dv for integration by part can be equal to uv minus, if we transpose this to the other side, that would be negative integral of v du, wherein v and u are two distinct functions. So that is the derivation of how we do integration by parts. All right. So without further ado, let's get started with some examples. So for example number 1, so let's have So the integral of, so sample problem number 1, so we have 3t plus 5, and then cosine t dt. All right. So if we're going to use substitution here, if we let u be equal to 3t plus 5, du will be equal to 3 dt alone. And if we substitute everything here, we still have with u and then a cosine t. Okay. So still have a function of t, and that's not applicable and that's not friendly in our equation. Okay. So we're going to apply integration by parts. So integration by parts, we need to remember the mnemonic LIATE. So L, I, A, T, and then E. Wherein L is logarithmic, I is inverse, A is algebraic, T is trigonometric, and then E is exponential. All right. So this will be the hierarchy of U. So the first should be logarithmic down to exponential. And then from exponential, that would be dv up to upwards to logarithmic. So therefore, U will be the one to be differentiated. And then dv will be the one to be integrated. All right. So for that case, we have there an algebraic and then a trigonometric. So therefore, we will let the trigonometric be our dv. So, and our 3t plus 5 can either go as dv or u. And since we chose our trigonometric to be dv, so we'll have no choice that the rest would be an algebraic function. So therefore, 3t plus 5 would be algebraic. All right. So I'm going to delete everything here. And then let's proceed with solving this sample problem. So therefore, we're going to integrate this by parts. So if we integrate this by parts, so we will consider the equation as components of two different functions. All right. So therefore, we let u be equal to 3t plus 5. And the derivative of u or du would be equal to 3 dt. Then, our integrand side would then be dv is equal to cosine of t. And the integral of cosine of t is equal to sine of t. All right. Such that we can now apply what we have derived or the formula. We have uv minus integral of v du. So we substitute everything here. So we have 3t plus 5. And then our v is equal to sine t minus the integral of what is our v, so that is sine t. And our dv is 3 dt. So 3 is a constant, so we factor that out here. So 3 dt. Then we put that out. So we have here 3t plus 5 sine of t minus 3 integral of sine t dt. All right. So rechecking this equation. So negative 3 integral of sine t dt is integrable. Okay, so if you can inspect this. So therefore, if you're going to integrate sine t dt, you can now directly integrate sine t dt such that we know that sine t dt, if we find the integral of sine t dt, so that is negative cosine of t plus c. All right. So the integral of 3t plus 5 cosine t will then be equal to 3t plus 5 sine of t minus 3 quantity negative cosine of t plus c. All right, negative and negative, that becomes positive. So therefore, the answer and the integral of this one is equal to 3t plus 5 sine of t plus 3 cosine of t plus c. And this is now the answer to our sample problem. So absorb. Okay. So let's pause for a short moment. And then let's now go to our next sample problem. So for our next sample problem, so we have here the integral of x squared e raised to x dx. All right. So if that's only x, so we can simply you substitute that, but in some cases, it's not applicable. All right. So we still apply integration by parts for this sample problem. So recalling the mnemonic, Liate. So we have here an exponential function, e raised to x. So therefore, definitely, we set this as our dv. And x squared is algebraic, so therefore, we let this our u. So therefore, we let u be equal to x squared. Our du now would then be equal to 2x dx. Then for integral side, we have dv equals to e raised to x. And what is integral of e raised to x? So integral of e raised to x dx is e raised to x plus c. So we only get e raised to x to get our v. So therefore, v is equal to e raised to x. All right. So we apply the formula uv minus integral of v du. So therefore, we have x squared e raised to x minus the integral of what's our v? So that is e raised to x. So therefore, we have e raised to x and our du is 2x dx times 2x dx. Let's fix this equation first before we proceed any further. So we have x squared e raised to x minus the integral of 2x e raised to x dx. All right. So we factor out 2 here. So we have x squared e raised to x minus 2 integral of x e raised to x dx. All right. So if we let u be equal to x, du is equals to dx. But this will just resubstitute to u e raised to u, du. And we cannot use direct substitution of x still. So therefore, we need to reapply integration by parts in this particular equation. All right. So we're going to apply integration by parts here. And we're going to again use this method. So for that case, we're going to apply again integration by parts. So for this one, so we let u be equal to, so algebraic is x, so therefore x. Du is equals to dx. Then our integrand part would be dv equal to e raised to x. Then integral of e raised to x is simply equal to e raised to x. All right. So don't forget the x. So therefore, we can rewrite this as x squared e raised to x minus 2, then quantity. What's our uv here? So that will be x e raised to x. Let's fix this first to avoid any confusion. So 2 in quantity. So x e raised to x minus the integral of v, which is e raised to x, and our du is dx. Okay, ex dx is now integrable. All right. So we're now going to proceed with our integration here. So therefore, this further reduces to x squared e raised to x minus 2 quantity x e raised to x. And what's integral of e raised to x? So that is simply e raised to x. So therefore, we have negative e raised to x, but we don't have c yet. All right. Distribute the negative sign. So we have x squared e raised to x minus 2x e raised to x plus 2 e raised to x plus c. And that is now the answer to this integral. So did you get it right? All right. So let's have one more problem after the sample problem. So it's advisable you take your notes or you take down notes while doing the sample problems. All right. So let's have another sample problem to further aid in your learning. So let's have another one. So we have ln of x dx. So number 3. So you have integral of ln of x dx. All right. So for ln of x dx, so we already have the formula for this one. So what's the formula for ln of x? But I want to show you how it is done. So for ln of x dx, so let me pause for a while. So for ln of x dx, so if we let u be equal to ln of x, our dv will be equal to dx. All right. So let's just derive the formula for this one so that to avoid confusion. So if you let u be equal to ln of x, our du will be equal to 1 all over x dx. And then we only have dx here, which is an algebraic function. So therefore, dv be equal to dx. And if we're going to integrate, so if we're going to integrate dx, so therefore our v would be equal to x. So applying the formula, uv, so we have x ln of x minus the integral of v, and our du is 1 all over x dx. So x and x gets cancelled out. So therefore we have x ln of x minus integral of dx. So integral of dx is simply equal to x. So therefore, the answer for this problem would lead to x ln of x minus x plus c. And that is now the derivation of the formula for the integral of ln of x dx, which came from the integration by parts. All right, so that's all for this short lecture series. So if you have any questions, so please don't hesitate to send me a private message. So hit that like button, hit that subscribe button if you think this lecture helps you out. So thank you for listening and thank you for watching this video. So hope to see you again on the next lecture. So see you and God bless.